In this video, we're going to introduce an alternative way of reporting regression coefficients. So far, we've only discussed what are called unstandardized regression coefficients. B0, our intercept, and B1, our slope, are unstandardized regression coefficients. Unstandardized regression coefficients describe the relationship between the predictor and outcome in terms of their raw units. If our outcome is scores on a kindergarten readiness reading scale, and our predictor is the number of hours a parent reads to their child each week, B1, the slope or effect of parent reading, will be the increase in reading scores for each hour of reading a parent does each week. As a result, the numerical size of the regression coefficient is inherently tied to the units of scaling we use. Think of it this way. If the slope is equal to 6, that means that for a 1 hour increase in parent reading, the predicted reading scores will increase 6 points. But what would happen if I change the scaling on my predictor to measure that time in minutes instead of hours? How many minutes a parent reads to their child each week? My slope now is the increase in my predicted scores for a 1 minute increase in parent reading, a much smaller unit. Now, a 1 minute increase in reading would only lead to a 0.1 increase in predicted reading scores. The slope would only be 0.1, not 6. But nothing's really changed. All I've done is rescale my predictor variable. The fact that the size of b depends on the scale used means you have to be careful concluding whether a b is large or small. You can make the value of b large simply by using a scale based on large-sized units, the impact of an hour of reading to your child, or you can make the value of b small simply by using a scale based on small-sized units, the impact of 1 minute of reading. When we get to multiple regression and have more than one predictor, we'll see a different problem. Because different variables reflect different constructs that may be measured using very different scales, it's impossible to compare the size of inherently different variables using unstandardized regression coefficients. For example, we might be predicting SAT scores and end up with regression coefficients that indicate the effect of hours of studying each day and dollars of family income and the number of AP courses a student takes. To try to compare those regression coefficients and see which has a larger impact on SAT scores is essentially comparing apples and oranges. In contrast, you can also have standardized regression coefficients. These are represented by the Greek letter beta. Standardized coefficients describe the slope or effect of a variable in standardized units, z-scores or standard deviations. The standardized regression coefficient indicates how many standard deviations the predicted score on the outcome increases with a 1 standard deviation increase in the predictor. In simple regression, you can convert an unstandardized regression coefficient b to a standardized beta by multiplying the unstandardized coefficient by the standard deviation of x divided by the standard deviation of y. Because standardized coefficients all use the same scaling, standard deviations, with standardized coefficients, it's arguably possible to compare the effect of different predictors. A 1 standard deviation increase in one predictor reflects the same degree of relative change as a 1 standard deviation increase in some other predictor, even if they're measuring very different things. But you have to be careful. Because beta incorporates the standard deviation of x and the standard deviation of y, the size of beta will vary simply because the standard deviation in our sample changes. For example, for a given association between x and y, if I only sample extreme values of x, my standard deviation for x will be large and my beta will be relatively large. But if the overall association stays exactly the same and I instead only sample a narrow range of x, My standard deviation for x will be smaller and my beta will be smaller. The actual size of the effect of that association doesn't change at all, but I can make the standardized beta big or small simply by how I choose to sample my participants. That can be a real problem. Some statisticians, in fact, argue that this is such a problem that standardized coefficients are of little value. Now, I wouldn't go that far, but it's important to remember that the size of our standardized beta can vary based on sampling, particularly if we didn't randomly sample across the entire range of values in our population. The unstandardized regression coefficient doesn't suffer from this problem, though. On average, the unstandardized coefficient will be the same regardless of how you sample. Pretty cool. Consequently, while standardized betas are useful when we're comparing different variables, and we will use them later when we get into path analysis and multiple regression, I'm personally in the camp that's a little more cautious about standardized betas, particularly again if you don't have a random sample across the range of scores in the population. So we're going to focus on unstandardized regression coefficients. Now, before wrapping this up, it's worth noting that in simple regression, where we have a single predictor, the standardized regression coefficient is in fact equal to the correlation coefficient. That may initially seem surprising, but if you think about it, it actually makes sense. They both describe the linear relationship between x and y in terms of standard deviations or z-scores. In addition to being kind of cool, it also means that all of the things that influence the size of the correlation coefficient, like how we sample our participants, will also influence the standardized regression coefficient. So just keep that in mind when designing your study and when interpreting standardized betas. Now, the fact that in simple regression, the standardized regression coefficient beta is equal to R has huge implications if you think about it. We just said that a problem with standardized regression coefficients is that you can rig the size of beta simply by picking only extreme scores to get a relatively large beta, or only scores near the average of your predictor in order to get a small beta, even if the actual association is the same. But if R is equal to beta, you can also make R big simply by sampling extreme values on your predictor. And if you can make R big by sampling extreme scores, you can make R squared big by sampling extreme scores. And that's a problem. The size of the correlation and R squared are influenced by your sampling strategy. You can rig it to a degree. As a result, some statisticians will also argue that R and R squared are meaningless unless you have a random sample. And again, I'm kind of in that camp. Now, this is one of those important take-home conceptual points that I want you to remember. I love R. I love R squared. We'll talk about both, particularly R squared, a lot. But unless you have a random sample or a sample that closely reflects the distribution of scores in the population, it's arguably a meaningless value. Ouch! Now, on that bright note, let's wrap up this video on standardized and unstandardized regression coefficients. And while people will often report standardized regression coefficients, just be certain to remember how they're influenced by the way in which the data were sampled. Okay? Bye for now.